Well, hello again, everyone. Today, what I want to talk to you about is sort of our opening discussion of working with regression in SPSS. Now, you're going to see that when we talk about regression, we can be actually covering a lot of different topics. What we're going to be focusing on in terms of our discussion is going to be what we sometimes refer to as OLS regression, or ordinary least squares regression. And we can approach regression in two ways, and we're going to only focus on one of them right now, the simpler of the two, which is what we're simply going to call bivariate regression. In other words, we're going to be doing a regression with one independent and one dependent variable. Now, this is going to be compared to where we're going to go next, which is going to be a discussion on what we refer to as multivariate regression, which is going to be one dependent variable and multiple independent variables. But for now, we're going to focus only on the bivariate regression. Now, the assumption about OLS for any either bivariate or multivariate regression is going to be that our dependent variable meets all of the criteria for us to be considered to be normally distributed. So one of the assumptions that we have to make with our data, and we should test that idea before we move forward, is that in fact we meet that criteria. Assuming that's the case, then we need to identify what our independent variable is going to be. And I'm using it singular here because we're still just talking about a bivariate regression. Now, one of the benefits of using regression as compared to many of the other different types of hypothesis tests that we've talked about is that there actually is a little bit more flexibility here in terms of what types of variables we can use in regards to the independent variable. So our dependent variable must be continuous, must be normally distributed, but our independent variable can be either categorical or in fact it can be continuous. Now, there are going to be caveats on both of those as well, but in terms of categorical data, we say it has to be at the nominal level, and it must only have, at least in terms of this type of analysis, it must only have two values, so it's either present or not present. So you can even see up on the screen in front of you, I'm using our state level UCR data, which you know has many continuous variables in it. In addition, you can see I've created a new variable here, which I've called Southern Region. And what that's actually a reflection of is, if you go back to some of the older works in the field of criminal justice, there was a belief about what they call the Southern subculture of violence, the idea that in some of the Southern states, violent crime was considered a bit more norm than it was in other states. And so I thought that would just be an interesting kind of throwaway idea here to put in regards to a categorical measure as well. So let's start off and take a look at what a bivariate regression is going to look like. So we're going to go to Analyze, and about partway down, you're going to see Regression, and it's right below the correlation option. Now, there are a number of different types of regression, and again, we're only focusing on one here. So what I want you to do is that second option here is linear. And I said to you before, OLS stands for ordinary least squares regression, but ultimately what it's referring to is a linear regression. Linear in the sense that there's supposed to be a linear relationship or a straight line relationship between our independent and our dependent variable. So let's select that. And now you're going to see that this is a little bit more complicated, particularly in light of the fact that most recently we talked about correlations, which was very straightforward. You can see we have room for our dependent variable. For the first time, you can see we have independent, and it even gives you here, right, independence, the idea that we can be putting in more than one, and we're not going to worry about that today. You can include selection variables, case variables, weighting variables, and again, none of that are we going to worry about today. We're just simply running a bivariate regression. So what I'm going to do, let's pull this out so we can see this a little bit more clearly, is during our discussion of correlations, we said that there is in fact a relationship between the property crime and the violent crime rates. So what I'm going to suggest is that we're going to try and explain our property crime rate, so we're going to make that our dependent variable, by using our violent crime rate. Now, what's interesting here, and this only applies to when we're talking about bivariate regression, is that ultimately I could treat it the other way around and my results are going to be exactly the same. One is going to be impacting the other, no other alternative explanations given. That being said, however, once we get into multivariate regression, that assumption is no longer valid. So I'm simply going to identify these two. I've brought them both over, and then I'm simply going to click on OK. Now, you get a lot more output here in a regression than you've seen in most of your other statistical hypothesis tests through SPSS. And each one is doing something a little bit different. So I want to go through this so we're all comfortable moving forward. Now, the first box here, variables entered and removed, there's not a lot going on. It's simply telling you this is your dependent variable, and this was, in fact, your independent variable. Now, as you can imagine, when we move from bivariate to multivariate, there'll be a little bit more information here. Now, things like variables removed in method, it's based on the idea that there are different types of regression where we can actually tell the program to select which of a group of variables to include based on certain criteria. We're not doing that. And in fact, in the field of criminal justice and most social sciences, we don't do things like that. Because usually we're trying to test some sort of theory. We're not what we might refer to as data mining, where we're simply letting the data make a decision about what should be included in the model. Now, the next two lines here, model summary and the ANOVA test here, and yes, there is actually an ANOVA as part of your regression. But we've already seen something like this before. Remember, with their t-test for independent samples, we actually had Levine's test for the equality of variances in there along with the t. So it's not doing the same thing, and we'll talk about in just a moment, but don't be surprised. Now, what the model summary is telling us is overall, how well does the data fit the model? Now, what does that mean? Well, it means something very simple. We've told the program that we can explain violent crime using property crime. And I apologize, I just said that backwards. We told the program we can explain property crime by using violent crime. So it's telling us overall, how well did violent crime do in explaining property crime? Now, it does that by calculating an R. Now, if you go back, and you can run this, I'm not going to do it, but if you go back and run the correlation, the Pearson's correlation between the violent crime and the property crime rate, you would get the value of 0.491 that's being reported here. So this is the same R from the Pearson's correlation that we saw earlier. Now, the R squared is actually an important value for us to understand. An R squared is literally squaring the Pearson's R. So if you were to multiply 0.491 times 0.491, you're going to get a value of 0.241. And what it's actually telling us is a proportion between 0 and 1. And that's what proportion of the variation in my dependent variable is explained by my independent variable, and in the future, independent variables, right, when we move to a multivariate relationship. So, in other words, from between 0 and 1, how much of the variation is explained in the dependent variable is explained by the independent variable. Now, if it's easier for you, and I know a lot of people do this, just multiply it by 100 and you can say the percentage. So what this is telling us is that 24% of the variation in my dependent variable of property crime is actually, or can be, explained by similar variations in violent crime. Now, that shouldn't come as much of a surprise to us. When we talked about the correlations, we said that there was a moderate relationship between these two. So we can see that playing out here. Now, if we wanted to increase that R squared, we could start thinking about including additional variables in the model. But for now, staying with the bivariate relationship. The adjusted R squared is an alternative way of calculating the R squared, which is based, or is more sensitive rather, to the number of variables in the model. When we move to multivariate relationships, you'll find that if you continue to add variables into the model, generally speaking, your R squared will continue to go up. The adjusted R square is going to be sensitive to that. And so one of the things that we often look for is whether there's a large difference between these two. Now, right now, there's not. I mean, the difference between them is 0.018. It's a very small amount. So we're not really concerned about it. And of course, we've only added one variable, so there really can't be much of a difference between these two. But overall, we can say that for right now, this model is relatively interesting in the fact that we can explain about 25% or 24% of the variation. Now, you might say that's not much, and you're right. To some extent, it's not. But it's a quarter of all the variation. And you're going to see in some of your examples later on, we can't really get up that high either. All right, so the third line is the ANOVA. Now, the calculation of the ANOVA here is done the same way that we saw in ANOVAs before. You can see sum of squares, mean squares, an F statistic, and then a sig value. The question you should be asking is, what is the test of? It's not a test of the relationship between the variable and the independent variable and the dependent variable. It's actually a measure of whether or not a statistically significant amount of variation in our dependent variable has been explained. In other words, does this model do a better job than random chance? And is it worth basically running as a model? So if our value is significant, if my sig value on the right-hand side there is below 0.05, then we would say this is in fact a statistically significant model. In other words, it's a research hypothesis test or hypothesis test of whether or not, and the research hypothesis being that the model with the variable is statistically significantly better explanation for the dependent variable than just using random chance. And we can see we've rejected the null hypothesis would be, it's just as good as random chance, and we're saying that this is doing better than random chance. In other words, it's a model worth running. It's a model that's telling us something interesting. If my ANOVA is not significant here, then generally speaking, I don't have much more I can really talk about in regards to the overall model. And again, here you're going to see that the relationship between the model, the ANOVA, and the next line with the coefficient is literally the same. But that's going to change once we switch to a multivariate model in the future, so it's important to recognize that. So, most interesting part of the output, the coefficient. So, if we come all the way down here to the bottom, you can see our dependent variable is property crime, and we have the violent crime rate here as well. Now, the constant, don't worry about that. That is going to be about where the intercept lies. But ultimately, we can ignore the row that has the constant listed. And the only one we're really interested in is the one that has a variable name, in this case, the violent rate. First, you can see that it's a simple t-test. You can see we have a t-test statistic of 3.7, much higher than what we would normally use as a cutoff of, say, 1.96. I know our degrees of freedom is much lower here, but still, you can see by looking at the sig value, we have our t-test statistic has surpassed the critical value. Our sig value is below 0.05, and so we would say there's a statistically significant relationship between violent crime and property crime rates. Now, over here on the left, you can see we've got the unstandardized coefficient. Now, we'll talk about the standardized coefficient later when we talk about multivariate regression, so don't worry about that right now. We'll come back to it. But the unstandardized coefficient is the one that we're really interested in. Now, in this case, you can see it is a value that is positive. And again, just like our discussion of correlations before, positive is telling us something. There is a positive relationship between these two variables. As one goes up, the other goes up. Now, more importantly, unlike the correlation where all we could say at the end of it was that there is a moderate or a weak to moderate or strong relationship between them, we can actually do a unit-to-unit comparison between violent crime and property crime. And the way we interpret it is this. As violent crime increases 1 unit, and we're always going to use the term unit here because things can be measured at different units. But in other words, since this is a violent crime rate, what we're really saying is as violent crime increases one violent crime per 100,000 in the population, we would see a corresponding increase in property crime of 1.021 per 100,000 property crimes in the data. Okay, and remember this is state level analysis. So not only does this tell us that as we go up one violent crime, we see a corresponding increase, a greater increase in property crime. By the way, that only makes sense. We always have more property crimes than we have violent crimes. If it was the other way around, it'd raise some concerns for us. But this is what the regression does for us. It tells us, is there a statistically significant relationship? What's the direction of the relationship? And then maybe even most interestingly, what does that relationship look like? So those three pieces of information, in addition to the ANOVA results and that R squared, tell us a lot about the relationship between our variables. Now, I want to do one more quick example here, because this was an example of an independent variable that was continuous. I want to run the same model. I'm going to close this, and I'm simply going to say, analyze. We're going to go to regression again. We're going to go to linear. And instead of using violent crime rates, I'm going to get rid of that. And then I'm going to go to that southern region variable that I created before. And again, this is a dichotomous measure. It's a yes or no question. This is whether or not the state fell in what we would call the Area 6 in regards to regions in the United States. So it's Texas, Oklahoma, Louisiana, and a couple of other states that are going to fall into what they refer to as the southern states. Now, what we're simply saying is it's a yes-no. You're either a southern state or you're not a southern state. It's a dichotomous measure. It's the nominal level of measurement. If you're a southern state, it's equal to 1. If you are not a southern state, it's equal to 0. And with that, we're going to say OK. Now, here you can see the setup is the same. We come down here and you can see right away our R squared is much smaller. Before we had an R squared of about 24%. Now you can see our R squared is less than 0.048. If we wanted to transform that to a percentage, we'd say it's about 4.8%. So much lower than what we were seeing before, about a fifth of it. Coming down here to the ANOVA, you can actually see, in fact, that the ANOVA is not statistically significant. In other words, this model really hasn't done a better job than just random chance alone in explaining the relationship or trying to explain the variation in our dependent variable of property rate. Now, coming down here to the coefficients, again, we ignore the constant, but you can see the same things happening here. The sig value is non-significant. In other words, there is not a statistically significant relationship between these two variables. You can see, however, it was a positive relationship, but again, meaningless because it's non-significant. In other words, this could be based simply on random chance. And you can see our t-statistic is much lower, 1.5. So there's one last thing we can try here. And in part, when we talk about that idea of the southern subculture, it's usually a southern subculture of violence. Now, I've used property rate here. So let's run this one more time, but instead let's take a look and see what happens if we use violent crime as my outcome variable. So I'm going to say analyze, regression, linear. I'm going to take property out. I'm going to move violent in, and let's see if it makes a difference. And in fact, you can see it really doesn't make any difference. Our R squared is still less than it's less than 0.05. By the way, it's not a significance test. I don't want that to be misinterpreted by the way I just said that. Our R squared is 0.05. So we're saying about 4.5% of the variation in violent crime rates explained by a state being considered a southern state according to the federal categories. You can see our ANOVA is still above the 0.05, so it's non-significant. In other words, there is not a statistically significant relationship. This model does not do a better job than random chance alone, or does not do a significantly better job than random chance alone. Coming down here, you can see we have a non-significant relationship. So even though it's a non-significant relationship, I want to take a moment here to actually talk about how we interpret that unstandardized coefficient. Again, I'm only going to say this as if it had been significant, recognizing it's not significant because my sig value is well above 0.05. But if it had been significant, the dichotomous nature means that that whole unit to unit comparison doesn't make quite as much sense. But what it is saying is that states that fell in the southern region, on the average, had 42 more violent crimes per 100,000 in the population than states that were not in the southern region. And in fact, if I scroll back up here for a second, I'm looking now at the results from the property crime analysis before, and we would say something very similar. States that fell within that southern category had, on the average, about 93 more property crimes per 100,000 than states that did not fall in that southern region. All right. I know I moved through some of this very quickly, but ultimately, these are the three. These are really the main points of using conducting a bivariate regression analysis: the model summary, the ANOVA, and then ultimately that coefficient comparison, that unit-to-unit comparison between our independent and our dependent variables. I hope you found this helpful, and as always, if you have any questions, please do not hesitate to contact me. Have a great day.